physiologically plausible geometry. And lastly, a colleague of mine adapted the fab at home with a 3D laser scanner, which is pictured right here, adjacent to the syringe dispenser. And the concept here was to explore sort of the very early stages of in vivo printing. In this case, it's definitely not in vivo. This is an actual, I think it's a cow bone. And the idea here is to extract and culture cells from the patient, create a portal through the body to access the damaged region, 3D laser scan the defect, use some kind of imaging technology to identify the geometry of the defect, and use maybe expert knowledge of the medical professionals to understand the cell types of the defect. And then with that geometry plan, repair actions, that is the shape that needs to be printed to fill up the gap, and then deposit biomaterial, living cells, maybe scaffolding, stiffener, that sort of thing in there to replicate or sort of repair the defects. So sort of in conclusion here, there are a number of challenges I can see in bioprinting, and these are sort of span across the more complex multi-material, regardless of what the materials are, whether they're biomaterials or non-biomaterials. But one of the challenges that all these processes suffer from is needing to have support material if you really want to have freedom of geometry. So you notice that the fish robot was a very simple extruded shape with very slight tapers on it and so on, so that it wouldn't fall over. But if you really want to do a vascular tree, you've got branchings and so on that you can't lay down in any nice way, so they'll have to be supported. And I know there are ideas out there for this, but this is often a challenge. Any really complex geometry needs a support material that you then have to remove afterward, and it can be quite difficult to remove it from any internal cavities without causing harm to the object you're producing. Process control on almost all these, even the $1 million machines, is really inferior, like relative to the controls that your car has for monitoring its own health. These machines have nothing, they have no brain. So as it is, you can build something, it takes 42 hours to print a small object like this, and in the last hour the machine has a failure and the part is garbage. And you throw away a lot of material, a lot of time. In addition, you have low geometric fidelity because the machine is not aware of the errors it's making while it's building them. So this is a kind of a big initiative to improve these systems. They're very slow. It's 8 to 10 cubic centimeters per hour in most of these systems, with a few exceptions. Most of the processes used are not friendly toward living cells. So in photo-cured cross-linked resins, there's often toxic photoinitiators, and there have been some experiments to identify like the bare minimum of toxic material, but who wants an organ that was grown in conditions of toxicity right from the start? It seems risky. So if a way were found to circumvent that, I'm sure that would be beneficial to everybody. And shear forces in, for instance, inkjet printing or extruding cells through a syringe often tend to cause damage to the cells. And lastly, and probably most significantly, the CAD tools to represent what we want to build are nowhere near capable of representing what we need to build to replicate actual human organs. So don't represent material properties, break down if you try to represent very complex structures, and cannot communicate effectively with the machines because there's no channel that effectively transmits all of this multi-material complex structural information. And I think with that, as Vladimir mentioned, commercial bioprinting is a reality. I think a lot of people recognize this a huge potential market. Medicine in the US is more and more of the GDP. It's like 25% of GDP now. That's a lot of money. So there's a strong initiative to conquer those challenges I just mentioned, and a number of people are working on it. And with that, I will conclude. Thank you very much. Obrigado.